In this video, we are going to understand recursion. But before we get started, let me tell you that there won't be any demo on data view. This is not completely on data view, but on a concept that is being used in data view. So we'll be talking about recursion. Then we'll understand why recursion causes stack overflow error and how can tail recursion help to remove this error, and then also understand how the tail call optimization helps the tail recursion to eliminate the stack overflow error. So let's get started. I have a function. This function is written in Scala. So this function calculates the sum of a number. For example, if the number is 2, it will calculate 2 plus 1 plus 0, which is 3. If it is 3, it will go in the backward direction, 3 plus 2 plus 1 plus 0, and give the output as 6. So this function takes in an argument which is of the type integer and returns an integer. And then I have a stack on the right side which will store all the stack frames. So let's see what I have done in this function. So when I call the function, it checks using the if condition. If the number is equal to 1, then it returns 1. If it is not, it continues calling the function until the number, which is the input, becomes equal to 1. So remember, any recursive function should have a base condition which tells when to stop, because if the recursive function does not know when to stop, it will continue forever until it ends up with a stack overflow error, obviously. So the base condition over here is that the input should be equal to 1. If it's equal to 1, then the control should go back from where it all started. So let's see this in action. Now when I call the sum function with input as 2, the control goes to the sum function. It checks if num, that is the input, is equal to 1 or not, which is not the case, right? It's 2. So it goes to the else condition, and then it again tries to call the sum function with input as num minus 1, which will be 2 minus 1 and 1. So it will call sum of 1, but there is a residual value num which is waiting for the output of sum to be calculated. And since we have this value num, it will be stored in a stack frame which will be waiting for this sum function to get evaluated. Let's see what gets generated into the stack. So we have sum of 1 plus the residual value 2 waiting for sum of 1 to be calculated. So now the function control goes back to the new instance of sum, and again it enters the sum function and checks if num equals 1 or not. So in this case we have passed sum of 1, so the num is 1, right? So this satisfies the base condition and it will return 1. So the recursion breaks over here, and in the another stack frame we have the value returned as 1. So this stack frame will return the control to the previous stack, that is the calling stack, and then the sum of 1 will be derived as value 1, so it becomes 1 plus 2, and the final value 1 plus 2 equals to 3 will be written back, and that gets printed on the console. So that is how a recursion works. It calls itself until a base condition is met. Until the base condition is met, the stack collects the frame, and when the condition is met, the frame gets popped out of the stack and the control comes back to the root stack, and then the value is returned. So this was a very simple example. Now what if I increase the size of the number? Like it's 2 over here. Let's increase the size of the number to 100. So I have the same function, just that the size of the variable is 100 as opposed to 2 in the previous case. So what happens? The same thing. It goes to the function, checks if the input is equal to 1, which is not. So it goes to the else condition and then creates a stack frame by reducing 1 from 100, creating 99, and we have the residual value as 100. Now since it's recursive, it's calling the sum function. It will go back to the sum function and start with the if condition. Again, 99 is not equal to 1. It comes to the else condition and again creates a frame with calling sum function with an input of 98 and residual value as 99. Again, it goes to the if condition, checks it, comes to the else condition, and then the same thing, it becomes 97. So this stack frames would continue to collect inside the stack until the sum value becomes sum of num, which is the num value becomes 1 and the residue becomes 2. So it will continue until that. So if we move ahead, we get another stack frame which is having 96 and the residue as 97, right? Now again, let's continue. And what do we observe? That it has exceeded the limit of the stack. Stack was only able to handle 4 frames, but we have got the 5th frame and there are many more to come, right? It has to go until sum of 1. So the stack has become full and it will give a stack overflow error. Well, in this case the example was very small, so for the sake of understanding I kept the stack size as very low, but in actual coding the stack size would range around 200 or 300 or maybe 500, and beyond that it would give a stack overflow error. So when you code such function and give 100 as an input, it will for sure work fine, but when the values reach to like 10,000, 100,000, then there are chances you would end up with a stack overflow error. So if we notice, the residue value is the problem, because the residue value is causing the function to wait. The stack frame waits for the sum to get evaluated so that it can be added to the residue 100, right? So if we remove this, then it could be of some help. So that is what tail recursion does. Tail recursion says that the recursion should be the last statement of your function. After that there should be no operation. Like in this case, sum of n plus 1 should be the last statement. The plus num should not be present. It's the plus num that is causing the function to wait, and that is why we are accumulating all the stacks and leading to a stack overflow error. So in this case the space complexity of the function is also very high. It becomes O of n, and time complexity is obviously O of n depending on the number of iterations you have to do. So space and time complexity both are bad in this case. So let's see how we can make the space complexity better and eliminate the stack overflow error using tail recursion. So in this slide I have slightly modified the sum function. I have an added argument called as ACC, which stands for accumulator, and it's of type integer. I'm passing this argument. So what this argument will do is it will store the output of the previous step, thereby eliminating the residue. So we are not having any residue left, but instead that value is being passed to the next iteration of that function and used accordingly. So let's see this in action. So I'm calling the sum function. It goes and checks if the input is equal to 1, if 3 is equal to 1, which is not the case. So it goes to the else condition, Then it checks, it calls the sum function, num minus 1, 3 minus 1, which becomes 2, and accumulator is 1, so 1 plus 3 becomes 4, and that 4 value and 2 value will be passed to the sum function. So what do we get in the stack? We get sum of 2 comma 4. So the residue value, instead of being outside, we just removed that residue value, and instead we are using an accumulator to pass the values to the function, right? So now again the call goes to the function and it checks if num is equal to 1, which is not the case. 2 is not equal to 1, so it comes to the else condition, and now what it has done is it has sent 1 and 6. Why did it do so? Why the other stack didn't generate? Because we don't need the value, right? There's nothing waiting, there's no residue or anything waiting for it. So instead what we did is we just replaced the stack, right? But if you do this in Java, there will be another stack created. Instead of this stack replacing, there will be another stack created, because there is a concept which will come in the next few minutes, but another stack gets created. But since it's in Scala, the stack is not getting created. So what happened is the stack got replaced, the 2 comma 4 of sum got replaced with 1 6. So the accumulator is updated with the new value, and the new value is being passed as an input. So now when the function gets called again, the num is equal to 1, right? 1 is equal to 1, and it returns the accumulator value, which is 6, and we get the value. So now an important concept to understand over here is the stacks are not getting added, but instead getting replaced. Now there are a few conditions for this. This replacement of stack is only possible when you use a tail recursion, which we have done in this case. The recursive statement is the last statement of the function. After that there is no work to do, right? So this is the last statement of the function, so this becomes a tail recursion. And since we have no residue left, there's no point of holding the stack, right? If there was some, as opposed to the previous method, there was a residue left which was waiting for the sum function to return the value. But in this case we have no residue waiting for any value, right? So we can safely remove this, but instead pass this value to the next iteration, like 1 and 6 has been passed to the next iteration. So the stack can be removed safely. And for this stack to be removed safely, the execution engine on which your program runs, that should support tail call optimization. So Scala, which is used under the hood by DataView, supports tail call optimization by default. So that's the reason it's able to replace the stack. But if you try the same code in Java, you would not notice any visible difference. It will still throw the stack overflow error, because the stack will still get accumulated and won't get replaced, because Java does not support tail call optimization. And it's same for all other languages that do not support tail call optimization. So for the tail recursion to work properly, ensure that your recursive call is the last statement of your program, and the execution engine supports tail call optimization or TCO. Well, now enough of theory, let's see this in action. So let's go to a Scala editor, and in this Scala program, what am I doing is I have two functions. One is the function that supports tail recursion, and other one does not support tail recursion. It is a normal recursive function. So what I'll do is I'll first call the non-tail recursive function, which is also called as a head recursive function. So I'll pass the input as 3 and execute it. Let's see the output. The output is 6 as expected, right? Now let's try this with the tail recursive function. It takes 2 arguments. One is the accumulator, so let's give it as 1. And we get the same output, right? Now what I'll do is I'll just increase the input. I'll now call the head recursive function with value as like 10,000 maybe. Yeah, let's call with 10,000. So we are getting some value, right? Let's add one more 0, make it 100,000. And we ended up with stack overflow error. So it's quite visible, right? When the input increases, the stack is unable to handle, because there are stacks which are getting accumulated and not getting released, not getting popped out. So what if I now call the tail recursive method? Let's give an accumulator as 1 and let's see if we get the value. Yeah, we got the value, right? So Scala supports tail call optimization, and because of tail call optimization we were able to get the value. Due to this TCO, the stacks were effectively getting replaced rather than getting piled up upon one another. Now to demonstrate the same thing, I have it in JavaScript. I have made 2 functions. One is the normal one is the head recursive function and another is the tail recursive function. So let's first try with the head recursive function and let's try to run this. So I'm getting not a number. Okay, let me just try to remove this function and then let's try. Yeah, so we are getting the value as 6, right? Now let's just increase this value like maybe 1000. We are getting the value. Let's make it, add one more 0 and make it 100,000. Still getting the value. Let's increase the 0 and then we get maximum call stack size exceeded. Now let's change the solution to this one, which is the tail recursive solution, and let's see if we are able to get any values. So now let's do the same thing. Let's try with a small value and we are passing the accumulator as 1. We get value as 6. Now let's change the value to 10,000. We get the value. Now let's make it as 100,000. Yeah, the stack call size exceeded. Now did you notice, even though we had a tail recursion over here, we were not able to get the value. We encountered a stack overflow error, as opposed to coding in Scala where we didn't encounter a stack overflow when we went with tail recursion. This suggests that even if you do tail recursion and the tail call optimization is not enabled in the execution engine, you are going to land up with stack overflow error. So JavaScript with the introduction of ECMAScript 6 has the ability of tail call optimization, but there are some preconditions that has to be established for it to work. So in this case it's not there. So even though we use the tail recursion method, we landed up with the stack size exceeded error. Now what we can do is we can also try to see how the stacks are getting generated in the browser, so that we get a little better understanding. So what I'll do is I'll just copy. I've added a debugger to this function so that we can check the values step by step, right? So let's copy this function and let's open a new tab and let's open inspect. Let's go to the console and paste the code, hit enter. So the debugger has started. You can see paused in debugger, right? And you can see the call stack over here. So it's the stack has one stack frame, which is sum. Now if I run this code, let's move, and it goes to the return else, return sum of num minus 1 plus num. So this is a non-tail recursive, which is head recursive version, right? So it will store the stack. So let's move forward, and what we can see, a new stack got added, right? The stack was there and a new stack got added. Let's hit it again. It goes and checks the condition. The condition is false, so it goes to the else condition, and then it encounters a recursion and then adds a third frame in the stack. Similarly, it will go again, go to the else condition, call the recursion, and the fourth stack frame gets added to the stack, right? Now again the same thing. Let's come back and encounters recursion. Now we can see the fifth frame is getting added to the stack. Let's move ahead, and what do we see? Num1 is equal to 1. It's time for the fifth stack to be removed. So it gets, so now the fifth stack got removed and we are left with only 4 stacks. So the control is coming back to the root stack, right? All the stacks are getting popped off now. Now if we move ahead, again it's stuck at the return statement because it's now traversing to the root function which had called it. So it now again the third got eliminated, now the second, and now the final stack gets eliminated and the flow ends. And what we can see, we see the value 15, right? Now let's try with the tail recursive method. Now let me add a debugger over here, debugger, and then I'll do a console log. Let's keep the value as 5 because it will get lengthy. Copy this, refresh the page and paste it. Now let's see what difference can we see when we make a tail recursive call. So again we have a stack with 1 frame. Let's run this. Num is not equal to 1, so it will go forward, comes to the return statement, but then encounters a recursion and the stack frame got added. So this is where the change happens. If it was a tail call optimized engine, this sum stack frame would have got replaced by the new stack frame, which didn't happen in this case, right? It just blindly added the stack frame, a new stack frame, whereas we don't need this stack frame anymore, but it still is adding this without any use. So that's the problem. When the execution engine is not TCO, tail call optimized, it will continue adding the stack, and even if you go with a tail recursive method, you are going to end up with stack overflow error. So the important point over here is, to make a recursion avoid stack overflow error, you should have 2 things. First is use tail recursion by making the recursive statement as the last statement of your function, and ensure that the execution engine has tail call optimization enabled. So well, that's it for this video. I hope you would have found the concept useful, and we are going to use this concept in the next topics on data view. So thanks for watching.